January 1942 settled over Seattle with a cold, grey heaviness that seeped into everything, into the docks, into the streets, and deep into the sprawling steel ribs of Boeing Plant 2. Inside the factory, thousands of men and women worked beneath a haze of aluminium dust and fluorescent lights. Pneumatic rivet guns hammered in chaotic rhythm, sending vibrations through the concrete floor and rattling the windows like distant artillery. The air felt alive with pressure, urgency, and fear. Across the length of the factory stood 63 unfinished B-17 bombers, rows of skeletal fuselages and half-skinned wings stretching toward the far wall like the ribs of metal beasts frozen mid-creation. They were supposed to be symbols of America's industrial might. Instead, to the Army Air Forces, they looked like stalled promises. The United States needed bombers, hundreds of them, thousands of them, but production had slowed to a crawl. During the first 6 weeks of 1942, Boeing had delivered 9 aircraft. Not 90, not 19, 9. General Henry Hap Arnold, commander of the U.S. Army Air Forces, walked the factory floor on January 15th with a tightening jaw, his boots echoing against the concrete. Every unfinished bomber reminded him of the war slipping out of America's grasp. Without bombers, the U.S. had no air campaign. Without an air campaign, Germany's factories, oil plants, and supply lines would operate without interference. And without crippling those targets, any invasion of Europe would cost oceans of blood. In that cavernous factory, Arnold gathered Boeing executives and delivered his verdict. If Boeing did not fix this disaster, America's entire strategy for defeating the Axis would collapse before it ever began. Factories, manpower, raw materials, none of it mattered if the planes themselves could not be built fast enough to reach the sky. This wasn't just a production problem. It was a national emergency. Boeing's managers knew that something had gone terribly wrong, but the problem wasn't obvious. They had manpower, 30,000 workers hired in a matter of months. They had materials, aluminium, arriving daily, crates of tools stacked to the ceiling, pneumatic guns, drill presses, fasteners, jigs, and templates. They had motivation. Every man and woman in the building understood what was at stake. But the B-17 itself was too complex for wartime assembly. Its wings required over 12,000 rivets per side, each one placed with perfect coordination between a riveter and a bucker, a worker positioned inside the wing, holding a heavy steel bar behind each rivet as it was hammered in place. The entire process was a dance of precision, and under wartime pressure, the choreography had collapsed. Philip Johnson, Boeing's production manager, walked the line every morning before sunrise. He saw the same nightmare every day. Workers stepping over each other to reach rivet lines, hoses tangling, positions blocked by other crews, inspections backing up, and aluminium sheets expanding under body heat until tiny misalignments forced drill-outs and rework. Johnson finally timed an entire wing assembly from start to finish, 20 hours and 14 minutes, just to finish one wing. At that pace, Boeing could hire the entire city of Seattle and still never hit the Army's production targets. The blueprint was perfect, but the process was broken. The engineers who designed the B-17 rivet pattern had followed structural theory. Rivets were arranged in long, parallel rows running from the leading edge of the wing toward the trailing edge. Each row reinforced the next. Each line of fasteners aligned with calculated stress paths and load trajectories. Structurally, it was sound. Practically, it was unworkable. Workers couldn't fit around the structure without blocking each other. Riveters couldn't begin row 2 until row 1 was fully inspected. Row 3 waited for row 2. Row 4 waited for row 3. Every phase was chained to the next, and every delay multiplied across 12,000 rivets. This was the bottleneck that held back the entire air war. And it wasn't just technical, it was human. Cramped quarters, fatigued workers. Fatigue caused timing errors. Timing errors meant loose rivets. Loose rivets meant more rework. Rework meant longer assembly. Longer assembly meant hotter metal. Hotter metal meant misaligned holes. Misaligned holes meant even more rework. Every weakness fueled the next. The blueprint didn't account for exhaustion or tangled hoses or 20 people trying to work in the same square meter of space. Boeing's engineers had done their job, but the battlefield had shifted from the drawing board to the assembly floor, And the rules were different here. The wing was perfect on paper, but paper didn't have to build it. Into this crisis stepped a man almost no one noticed. His name was Frank Shamansky. 31 years old, quiet, short, and unassuming, he worked on the swing shift from 4 in the afternoon until midnight. He wasn't an engineer, he wasn't a supervisor, he was a riveter, one of thousands. His hands were stained with aluminium dust, his coveralls worn and oil-smudged, his boots scuffed from long nights on the factory floor. But Frank had something that textbooks couldn't teach. He watched. While other workers focused on their assigned sections, Frank watched patterns. The way workers collided around the same rivet lines, the way buckers struggled inside cramped cavities, the way hoses got knotted every time two teams switched positions, the way inspectors stalled entire rows, the way the sequence itself created choke points nobody could avoid. He noticed that nearly every delay could be traced back to one fact. The engineering blueprint forced everyone into the same physical space in the same order. Everything was sequential, everything bottlenecked. Frank's mind returned to something simple from his days installing door panels at Chrysler. When they assembled car doors, no one worked in straight rows. They started from multiple corners at once because it prevented workers from bumping into each other. Workers stayed out of each other's way, and the job went faster. What if the same logic applied here? One night during his break, Frank sat alone on an overturned parts crate, eating a cold bologna sandwich as he stared at a finished wing section being moved to final assembly. Something about those long, straight rivet rows bothered him. They treated the wing like a flat, two-dimensional sheet, but the wing wasn't flat. It had depth, cavities, ribs, spars, and access panels. It was a three-dimensional structure, and maybe the rivet pattern should reflect that. Frank pulled out his pencil and began sketching on the back of his time card. Not rows, clusters. Rivet clusters placed around ribs where workers could easily reach from inside and outside, then connecting those clusters in radiating, almost organic lines that followed the contours workers could actually access without bumping into each other. It looked wrong in every way Boeing had taught its workers to think. Chaotic, asymmetrical, uneven. No engineer would ever approve it. But as Frank traced the pattern with his fingertip, he saw something astonishing. 5 workers could rivet simultaneously, without touching, blocking, or waiting for each other. 5 zones, no overlap, no congestion, no need to wait for the previous row. A wing that took 20 hours might be done in 2. Frank knew what would happen if he showed it to the wrong person. He could be laughed off the floor. Worse, he could be reprimanded for questioning engineering specifications. In 1942, the hierarchy at Boeing was absolute. Engineers designed, managers supervised, workers obeyed. But Frank had the fortune, or fate, of showing his sketch to a man who actually listened. His shift supervisor, Bill Hendricks, had worked his way up from sheet metal laborer to overseer. When Frank nervously handed him the crude drawing, Hendricks stared at it, silent for a long time. Then he shook his head. "This breaks every structural principle we use," he said. "The rivet rows aren't there because they look nice. They're positioned perpendicular to stress lines so the wing doesn't tear itself apart under load." Frank nodded. He didn't know structural engineering, but he knew enough to guess that what he'd drawn contradicted a decade of aerospace design. Then Hendricks said the sentence that changed the course of the war. "Maybe the problem isn't the workers failing the pattern. Maybe the pattern is failing the workers." He explained something revolutionary. The theoretical rivet rows were only superior if installed perfectly, but perfection collapsed under fatigue, congestion, misalignment, and the messy reality of wartime manufacturing. A rivet pattern that was theoretically weaker might actually produce a stronger wing if it allowed flawless installation. It was an insight no engineer had even considered. Hendricks folded the sketch and said, "I need to show this to someone who's desperate enough to try it." That someone was Assistant Production Manager Donald Douglas. Desperate didn't begin to describe him. Douglas was weeks away from losing his job. Boeing was weeks away from losing the B-17 program entirely. If production numbers didn't improve by March, the government would shift contracts to other manufacturers, and the Flying Fortress, the bomber meant to smash the Nazi war machine, might die before it ever reached the fight. Douglas looked at Frank's sketch, shook his head, and said it looked like garbage. But when Hendricks showed him 6 weeks of time logs proving that not one crew had ever broken the 20-hour barrier, Douglas stared at the page in silence. If the rivet rows were structurally perfect but industrially impossible, the entire program was doomed anyway. Douglas approved a secret test. No engineering authorization. No official documentation. No senior management oversight. A forbidden experiment on graveyard shift. On February 21st, just after midnight, a damaged wing section, already disqualified from flight, was pulled onto the assembly floor. Frank arrived early with 4 of the most reliable riveters in the factory. They studied the pattern Frank had refined over 3 days. Zones were color-coded, tasks were divided, access points were chosen to avoid collisions. The sequence was unlike anything anyone had ever seen. At 12:14 a.m., the first rivet gun fired. What happened next didn't look like an assembly process. It looked like controlled chaos. Workers operated in different cavities at different angles on different surfaces. No one waited, no one crossed paths, no one stopped for inspectors, no hoses tangled, the metal stayed cool, the holes stayed aligned, every rivet seated cleanly. 2 hours and 7 minutes later, the final rivet was driven. The test wing was complete. Quality Inspector Jimmy Chen examined it, fully expecting to reject half the work, but the rivets were perfect. 11 needed adjustments compared to the usual 140. Chen thought it had to be a mistake. The wing then endured a full structural stress test. It reached the required 6.2 GS, then 7, then 8, then 8.4. It survived loads beyond the design margin without permanent deformation. Rivets remained seated, sheets remained flush. The forbidden pattern worked, and it was stronger than the original. By dawn, a decision had to be made. Keep this secret and risk nothing, or use it and save everything. For Boeing, for the Army Air Forces, and for the war, the choice was obvious. The assembly revolution had begun. Dawn crept slowly across Seattle on February 21, 1942, casting a pale gold sheen across Boeing Plant 2 just as the night crew finished sweeping aluminium shavings from the floor. The factory's fluorescent lights buzzed overhead, still bright despite the new sunlight pushing through the high windows. The workers looked exhausted, but beneath the fatigue was a strange, electric expectation. Something had happened in the night that none of them fully understood yet. The secret test wing still sat in Building 7's structural hall, mounted loosely on the test frame, quiet after surviving loads that should have warped it beyond repair. The technicians who had witnessed the impossible were still whispering about it when the first day shift supervisors arrived. Donald Douglas didn't wait for the day shift to settle. He marched through the factory with the thick folder of test results under his arm, his coat unbuttoned, his hair disheveled from lack of sleep. He had been awake nearly 24 hours, but adrenaline kept him moving. Every page in his folder was dynamite. If anyone saw it except the man he intended to show, he might lose his job before he could explain. He found James Murray, Boeing's vice president of operations, in his office overlooking the main assembly line. Murray had barely set down his morning coffee when Douglas placed the folder on his desk. "What is this?" Murray asked. "The solution," Douglas said, "if we move now." Murray opened the folder. The first page showed the assembly time, 2 hours, 7 minutes. He blinked twice, thinking it was a typo. The next page displayed the structural stress chart. The surviving numbers didn't make sense. Rivets weren't supposed to hold under those loads with that pattern. He flipped to the inspection notes. Only 11 rivets requiring adjustment. Murray looked up. Douglas didn't flinch. "You're telling me," Murray said slowly, "that you assembled a B-17 wing in 2 hours with fewer defects than a 20-hour standard assembly?" "Yes, and this," Murray tapped the pattern sketch, "is what did it." "Yes, and you did all of this without approval?" "Yes, Murray leaned back in his chair and exhaled a long, heavy breath. The enormity of what Douglas had done washed across his face in waves: rage, disbelief, shock, and then something else: possibility. "Who designed this pattern?" Murray finally asked. "A riveter," Douglas said. "Swing shift, name's Frank Shamansky." A silence hung between them. Then Murray stood. "Get him," he said. Within 30 minutes, Frank stood in Murray's office, still in his work clothes, his hands blackened from the previous night's labor. He looked uncomfortable in the executive space, as if he'd stepped into a world he wasn't supposed to see. Murray held up the pattern. "Oh, you made this?" Frank nodded once. "You know, this contradicts almost everything our engineers believe about structural distribution on this aircraft," Murray said. "Yes, sir. And you're aware that if this fails in combat, if a wing tears off because of this new pattern, it could cost American lives?" Frank swallowed hard. "Yes, sir." Murray studied him for several seconds, then set the paper down. "And you're certain," he asked quietly, "that this works?" Frank hesitated, not because he doubted the results, but because certainty wasn't part of his nature. He spoke only what he knew. "Sir, I'm certain that this pattern lets us build it right, and building it right makes it stronger than building it perfect." Murray nodded slowly. That was the answer of a man who understood reality better than theory. An hour later, Murray convened an emergency meeting with Boeing's senior leadership. Engineers filled one side of the room, supervisors on the other. Oliver Eccles, the head of engineering, sat stiffly with his arms crossed, already suspicious of whatever had brought everyone together so abruptly. Douglas presented the test results. He didn't embellish, he didn't dramatize, he simply explained. The room shifted restlessly. Then Frank's sketch appeared on the projector. Eccles erupted on sight. "This is chaotic nonsense," he barked. "This violates basic principles of load path theory. Rivet spacing isn't even uniform. Stress lines have been completely ignored. This is not engineering, it's vandalism." Murray raised a hand. "Oliver, sit." "Sit," Eccles echoed, incredulous. This amateur scribble will get people killed. I won't be responsible for." "You won't be," Murray interrupted, his tone cold. "I will." The room fell into stunned silence. Murray stood and walked to the front. "We do not have the luxury of building perfect wings," he said, his voice steady and low. "We need buildable wings, surviving wings, wings that carry bombs to Germany and bring our boys home. The enemy is not rivet spacing, the enemy is time." He tapped Frank's pattern on the screen. "This pattern gives us time back." Eccles shook his head, furious. "You can't just throw out decades of engineering theory." "We're not throwing away theory," Murray replied. "We're acknowledging reality, and reality is killing us." He paused. "This pattern goes into full production in 4 days." The room erupted in protests. Engineers stood arguing over structural risk. Supervisors shouted over scheduling conflicts. Someone insisted the War Production Board would never approve it. Another demanded that Congress be notified. The noise escalated into a storm. Murray let it burn for a few seconds, then slammed his palm on the table. "The army will not wait. Germany will not wait. We will not wait." The room fell silent. "This is happening." The next 96 hours were unlike anything Boeing had ever attempted. Plant 2 transformed into an improvised academy for a new assembly philosophy. Frank, still stunned by the sudden attention, spent nearly every waking hour teaching teams how to follow the pattern, how to think in zones, clusters, and access corridors rather than rows. Workers gathered around him, scribbling notes, sketching their own color-coded maps, asking questions about angles, timing, and coordination. Frank explained everything he'd learned through watching the process for months. Not theory, not equations, just the simple truth of how the wing's geometry interacted with the human body. He demonstrated how to position hoses to avoid tangling, how to rotate buckers to reduce fatigue, how to use natural access points to minimize movement, how to match the cluster order to the way workers naturally flowed across the skin. The fascinating part was what Frank taught. It was how quickly everyone understood. Every worker had lived the frustrations of the old method. The pattern wasn't just a rivet sequence, it was a map of their lived experience. By February 25th, 42 wing stations were ready. Workers stood at their positions, their faces set with determination, knowing they were about to attempt something that would either save the production program or collapse it completely. The first official wing assembly under Frank's method began at 0800. Observers crowded the walkways above the line. Engineers tracked stopwatch times from every angle. Supervisors monitored each riveter. Reporters from the Army Air Force's film unit positioned cameras discreetly behind welding shields, documenting this unannounced experiment for potential wartime propaganda. The plant floor erupted in noise as the rivet guns fired. 5 workers, 5 zones, simultaneous, coordinated, fluid. The choreography of chaos from the secret test was now a symphony. No one waited, no one collided. Rivet after rivet seated smoothly. Aluminium sheets aligned perfectly. Buckers inside the wing called out confirmations through the framework with rhythmic consistency. Inspectors could barely keep pace. For the first time in factory history, quality control slowed the production because the production was too fast. 90 minutes in, half the wing was done. 2 hours in, it was complete. The quality report arrived 20 minutes later. 17 rivets flagged, all minor, all fixable, 7 times fewer defects than average. The wing passed structural inspection before lunch. By nightfall, 2 more wings had been assembled using the new pattern, both under 3 hours, both with record-breaking quality scores. The dam had broken. Boeing Plant 2 switched entirely to the Shamansky pattern within 48 hours. From that moment forward, everything accelerated. Wing bottlenecks vanished. Fuselage sections matched wing output exactly. Tail assemblies, which had often piled up waiting for mates, now integrated immediately. The entire bomber line, once a snarl of delays, became a flowing river of aluminium and fire. March production doubled. April doubled again. By June, Boeing was producing more bombers in a single month than it had built in the entire previous year. But the true impact of the Shamansky pattern became clear not in Seattle, but across the Atlantic. In the early morning hours of October 2, 1942, the 8th Air Force launched its first raid of more than 100 B-17s. Their formation stretched nearly 30 miles long, a glittering razor of silver slicing through the cold English sky. German radar stations detected the approaching mass. Fighter squadrons scrambled. Anti-aircraft batteries calibrated. Luftwaffe commanders stared at their screens, shocked. Never before had the Americans launched a raid of this scale. The bomber crews felt it first, the unimaginable strength of flying inside a formation so vast that the defensive firepower merged into a single, impenetrable wall. The German fighters that dove into the formation were shredded by thousands of converging .50 caliber rounds. The Luftwaffe pilots called it the flying anvil. What the Germans didn't know was that these bombers existed because a factory worker had redrawn the pattern of 1,000 rivets. Each bomber represented a wing built in 2 hours instead of 20. Each bomber represented a crew that would live because their plane was ready for combat months earlier than Hitler expected. Each bomber represented another step toward the collapse of Nazi industry. And the momentum didn't stop. By spring 1943, the 8th Air Force was launching raids with 300 bombers, then 500. By the fall, American heavy bomber strength exceeded anything Germany could replace. Rivets beaten into aluminium in Seattle were tearing holes in German production lines thousands of miles away. Inside Boeing Plant 2, morale soared. Workers understood that every improvement, every accelerated hour, every perfect rivet mattered. Newspapers published glowing headlines. The War Production Board sent photographers. President Roosevelt himself referenced America's arsenal of democracy and praised the miracle of air power. But inside the factory, the truth was more humble. Workers knew exactly who had unlocked this miracle. They knew who had broken the bottleneck and reshaped the future. They knew it was Frank. He walked the floor quietly, still carrying his rivet gun when not called into meetings. He trained others patiently, without pride. He moved through the plant as though nothing had changed. But everything had changed. Engineers now asked him questions. Supervisors now sought his advice. Riveters treated him with a mix of respect and awe. Boeing executives began involving manufacturing workers earlier in design discussions, something unthinkable just months earlier. For the first time, the people who built the machines were being heard. Frank's pattern had done more than accelerate production. It had reshaped the relationship between engineering theory and manufacturing reality. It had forced Boeing, and soon the entire aerospace industry, to recognize that the person holding the tool might see problems the person holding the blueprint could not. And the war still had years to go. More discoveries lay ahead, more challenges, more production miracles, more battles won by the speed and strength of American industry. But in the spring of 1942, the tide had already turned. Not in the skies over Europe, not in a war room in Washington, not even in the mind of a general. The turning point happened on the night shift of Boeing Plant 2, when a riveter looked at a problem that everyone accepted and refused to accept it. What he created wasn't just a pattern. It was a revolution built one rivet at a time. By summer of 1942, Boeing Plant 2 no longer resembled the chaotic, gridlocked factory that had once struggled to complete a single wing in 20 hours. The transformation was total. The aisles that used to be choked with half-finished components were now clear, open, and moving constantly. Crates of aluminium skins flowed through the plant with the coordinated rhythm of a living organism. The thunder of rivet guns blended into a rolling pulse that seemed to beat in time with the war itself. From the catwalks above the factory floor, executives and military inspectors could now see something almost startling in its precision. The entire line moved with a sense of purpose rarely found in wartime manufacturing. Where bottlenecks once paralyzed the line, now there was motion. Where inspectors once waited hours to review work, now they arrived early, almost racing to keep pace with the workers. It was as if every gear in the vast industrial machine had finally clicked into place. The new rivet patterns were pinned above every workstation. Colored diagrams showed the zones and clusters. Workers memorized their paths the same way soldiers memorized battle drills. The once confusing spaghetti of hoses, tools, and jigs was now organized with military precision. Hoses hung neatly from overhead rails. Tools had designated positions marked in bright paint. Buckers moved through the wing interiors with the practiced ease of dancers. Everything flowed. Everything worked. Yet behind this triumph was a quiet truth known only to the workers. The rivet pattern was more than a technical fix. It had restored something deeper: confidence. Before, workers had braced themselves for long, grinding shifts of frustration, fatigue, and unavoidable errors. Now they saw immediate proof that their work mattered and that their skill had power. They felt the pride of watching a wing that once took 20 hours now take 2. They felt the energy of being part of something bigger. And for the first time, Boeing's engineers saw it too. At first, the engineering department had treated Frank's pattern as a temporary production hack, something to be tolerated but not embraced. But as the weeks turned into months, something unusual began happening. Engineers wandered onto the shop floor, asking not just supervisors for feedback, but workers. How do you reach this cavity? Does this angle slow you down? Is this access panel placed correctly? Does the sequence feel natural? It was unheard of, and it was the beginning of a philosophy that would someday be called design for manufacturability, a philosophy that started not in a research lab, but in the lived experience of exhausted workers building too many wings the wrong way. The Szymanski pattern didn't just accelerate production, it forced a merger between theory and reality. And that merger would reshape the world far beyond Boeing. But before that transformation could unfold, the pattern faced its first true test, not in calm laboratories but in the crucible of war. On August 17, 1942, the U.S. Army Air Forces launched the first American heavy bomber raid from Britain against Nazi-occupied Europe. The target was Rouen-Sotteville, a French rail yard critical to German logistics. 12 B-17s lifted off from RAF Polebrook, their polished aluminium reflecting the cold morning light. Among those aircraft were bombers built with wings riveted under Frank's pattern. The change was invisible to the pilots. No one climbing into those aircraft knew that the internal network of rivets beneath their feet was arranged differently from traditional wings. They didn't know that the pattern they trusted with their lives had been sketched on the back of a time card. All they knew was that they were flying into danger. German radar detected the formation early, and fighter squadrons scrambled. But something unexpected happened that day. The new B-17 formations, supported by tighter production schedules and consistent aircraft availability, maintained perfect cohesion. Their defensive firepower was overwhelming. German pilots dove into the formation only to be met with a torrent of .50 caliber fire. Aircraft built on the backs of factory workers in Seattle were holding the line in the skies over Europe. The raid succeeded. But the bigger victory was the proof that American industry could keep pace with the demands of a global war. Back in the United States, production numbers soared. The Army Air Forces watched Boeing's output climb with disbelief. Commanders who once considered canceling the program now demanded more. General Hap Arnold personally toured Plant 2 again in July. This time he didn't criticize, he congratulated. He shook hands with riveters and machinists. He even asked a few workers about the new method he had heard rumors about. Frank was there that day, though no one introduced him. He watched from a distance as Arnold praised the workers and the leadership. Frank didn't mind. Recognition wasn't why he made the sketch. He knew what mattered was whose name was on it, but how many bombers reached the men who needed them. Still, the shift in culture soon reached him. For the first time since Boeing had opened its doors, the manufacturing floor had a voice. In late 1942, engineers called Frank into a meeting to discuss an unrelated assembly bottleneck in the tail section. They asked him what he saw, not what he thought according to theory, but what he observed with his eyes and hands. Frank made notes, walked through the line, and within a week proposed a new sequencing method that cut tail assembly time by 40%. His understanding wasn't academic. It came from intuition forged through watching the rhythm of work over thousands of hours. It came from respecting the limits of the human body, not just the tolerances of metal. Supervisors began sending trainees to him. He became a kind of informal instructor, explaining not just the pattern but the mindset behind it. Don't fight the structure, work with it. Don't force the sequence, feel the flow. Don't trust theory alone, trust the people doing the work. By the beginning of 1943, other plants had noticed. Boeing Wichita, Douglas Aircraft in Long Beach, Lockheed Vega in Burbank. All three were building B-17s. All three struggled with wing bottlenecks. Boeing sent copies of the pattern and training films showing the new method. Engineers from other factories traveled to Seattle to watch the process live. Several took detailed notes, sketching diagrams that looked more like creative geometry than traditional engineering layouts. But to the riveters, it made perfect sense. The Szymanski pattern spread, and with it spread the understanding that workers held knowledge no textbook contained. By March 1943, combined bomber production from all factories hit unprecedented numbers. Hundreds of B-17s rolled off the assembly lines every month. Assembly halls glowed with activity. Crates labeled for Britain, North Africa, and the Pacific left the ports in endless streams. This was industrial war, A war fought not just with rifles and planes, but with jigs, rivet guns, and intuition. The war in the skies responded. With more bombers available, the US could launch deeper and more frequent raids. The Luftwaffe scrambled to adapt. German fighter groups shifted east-west, trying to predict American strikes. Anti-aircraft defenses intensified, yet the bombers kept coming. Aircraft built with the new patterns saw the same combat stresses as traditional wings, and they held. Structural reports from field depots returned with praise. Fewer micro cracks, fewer rivet failures, fewer skin deformations after heavy G-load maneuvers. Engineers reviewing the data saw something extraordinary. Frank's pattern wasn't just as strong as theory predicted, it was stronger. The clustered rivets near ribs distributed force more evenly. The radiating lines acted like stress diffusers, channeling energy away from weak points. Where theoretical rows might have torn under side loads, the organic pattern behaved like reinforced fabric. Boeing began quietly referring to it as distributed load clustering. The name sounded scientific. Few knew it came from the mind of a factory worker. But the war did not slow down, and neither did Boeing. New bomber variants demanded new assembly tricks. The B-17F, then the B-17G with its famous chin turret, introduced new complexities. The wings stayed mostly the same, but the fuselage required new production logic. Plant 2 confronted new bottlenecks, but now they had a precedent: look to the floor workers. Frank continued offering insights, though he insisted he was just helping. He walked the lines with supervisors, identifying sequences that caused physical strain. He mapped new routes through cramped interior sections, reducing worker fatigue. He watched where workers hesitated and asked why. He saw problems before they became crises. The workforce trusted him because he spoke their language, the language of experience, not theory. Engineering began adapting designs earlier in the process. Drafting tables started incorporating feedback forms from riveters, buckers, and assemblers. For the first time in Boeing's history, blueprints were modified not just for performance, but for manufacturability. Then came the moment when Frank's influence reached beyond the B-17 program. In early 1944, Boeing began preliminary work on its next-generation jet bomber, the B-47. Swept wings, pressurized cabins, thin high-speed profiles. It was unlike anything Boeing had ever built. And this time, the engineering department formally invited manufacturing representatives to the design meetings. No one had ever done that before. Frank attended the first session in a small conference room filled with engineers, draftsmen, and planners. They spoke of stress factors, laminar flow, engine nacelle geometry, and high-altitude compression forces. Frank didn't understand half the terminology, but he understood the other half, the part where workers would be expected to build these wings under pressure. When engineers showed the proposed fastener layouts, Frank did what he always did: he watched. Then he asked a simple question. Can a bucker even reach that? The room fell silent, because the engineers hadn't thought about reachability yet, but they would now. This was the moment when the gap between theory and practice narrowed into a single shared mission. Engineers began studying worker positioning, tool access, fatigue arcs, and assembly flow as seriously as aerodynamic stress. They developed mock-ups with removable panels to test hand positions. They redesigned rivet lines to match ergonomic constraints. It wasn't glamorous, it wasn't dramatic, but it was revolutionary. That revolution spread. Douglas Aircraft applied work-first logic to the DC-8 airliner. Lockheed used the principle when designing the C-130 Hercules. Boeing relied on it when building the 707, then the 727, then the 747. Every major aircraft built in the second half of the 20th century carried the philosophy that emerged from a single night shift breakthrough. But Frank never sought acknowledgement. He received a commendation from the War Production Board in mid-1943, but no promotion beyond his production methods specialist title. When the war ended, the demand for aircraft collapsed. Workers were laid off in waves, and Frank, like many, quietly returned home. He worked at Ford for more than 2 decades. He lived a modest life. He never lectured at engineering schools. He never wrote a book. He never appeared in documentaries. He never claimed credit for reshaping an industry. Yet his influence remained everywhere. Every modern assembly sequence, every design review involving shop floor workers, every manufacturability meeting, every ergonomic layout of tools and access points, every robot-guided fastener map, all of them carried echoes of Frank's insight. That insight was simple. A design isn't complete until the people who build it can do so flawlessly. Industry forgot Frank's name, but they kept his wisdom. His pattern lived on, not in the exact lines of rivets he drew, but in the mindset he awakened. The truth that manufacturing is a conversation, not a command, that brilliance can come from any level, that experience matters as much as theory, that revolutions often begin not with executives in conference rooms, but with workers holding grease-stained tools, seeing what others miss. Even now, decades later, aerospace engineers still study the B-17 as a lesson in production philosophy. They learn about the transformation at Boeing Plant 2. They read about the shift from rigid design doctrine to flexible manufacturability. They hear how wartime urgency forced innovation. They analyze how workers and engineers collaborated to break bottlenecks. Most never learn the name of the man who sparked it. But every riveter, every machinist, every production engineer, every designer following modern sequences unknowingly reenacts a piece of his discovery. The truth is simple. Frank wasn't a genius, he was observant. He wasn't more educated, he was experienced. He didn't rewrite the science of structural loads. He simply recognized that perfect theory means nothing if people can't build it. The B-17, the flying fortress, America's most iconic bomber of World War II, owed its mass production, not to a breakthrough in metallurgy or to a $1 million research grant, but to the quiet logic of a riveter who refused to accept the way things had always been done. He changed a pattern, and that pattern changed the war.